here it is, right? I mean, that's the, oops, I'm in editing mode here. So that's the only string you need to know in order to securely communicate with the internet computer. Right, so, but let's talk about building stuff, right? How does code work on the internet computer? And first off, we really believe that smart contracts will lead the world. Well, software will lead the world, like everything will be software, but smart contracts are just a way better version of software because they're like in principle sovereign software, they're secure, they're tamper-proof, and so on and so forth. So that's why we are building the internet computer, because now with the internet computer, you have smart contracts that are powerful enough to actually run all of the world's software. So what is a canister? I mean, a canister, again, is a smart contract, but at the end of the day, it's a bundle of code, and the code could be written in Rust, TypeScript, Python, Solidity, Motoko, whatever at the end of the day compiles to WASM. So we use WASM, like what is used in the browser, just like as a sandboxing on the internet computer, just to have security, separation, and so on and so forth. And a canister also has like the data, so it's like a bundle of code and data, and the code and data is like one unit that is controlled by a principal, by a controller, and that one, I mean, it can also be black hole, of course, but that controller has full control over it. So it's not like on a cloud where maybe Amazon has control of it. No, like the control of the smart contract is the one that is charged here. It can then decide whether or not to upgrade. It can decide whether or what to do with the data and so on and so forth. But nobody else can have access to the data. So the access to the data is only via the APIs that the smart contract allows. And smart contracts on ICP, they actually, ICP gives you a ton of functionality that you don't find anywhere else. So for instance, in terms of memory, right? I mean, like if you are implementing on Ethereum, for instance, you have like 4K of memory on ICP, you have like 4 GB of heap memory. And I'm not even sure whether this number is correct. Actually, it's not correct. Let me change that. That's actually 400 gigabyte of stable storage at like $5 a year. You can implement it in Rust, TypeScript, Python, Solidity, Motoko. You can also use AI. So just are working on making AI to implement stuff here, so you don't have to do it yourself. Actually, you're not even bound by the block time, right? You can just keep running. It doesn't really matter the blockchain or block times. And not just like one thing under the hood that powers the whole thing. You can just go for quite a while until you get stopped. Of course, at some point the system has to stop you because making sure that you don't end in deadly loops and stuff like that. Smart contracts can also interact with Web 2, so they can serve HTTP because they have URLs. They can also be search engine optimization. So actually, you can Google for ICP smart contracts. They can call other URLs, so they can interact with the rest of the web. So you don't need oracles on ICP, right? Everybody can just make queries and get the result back. Again, too much to explain how this really works under the hood, but they can get information like that. Users can authenticate with passkey, so you don't need to have like wallets or install anything. All what you have on your phone actually makes is all necessary. Is all that is necessary. I mean, iPhones have this passkey technology. As I said, right, they can hold crypto. They have ECDSA, Schnorr. Actually, Schnorr already works. Schnorr and EDSA keys as well, so you can talk to any blockchain really these days, and much more. So I guess you can search online on the documentation. And actually, so something that we just did actually is very cool. You can actually go to icp.ninja, which is sort of this code editor, but it's actually a bunch of samples that you can click on, and then you can see the code, and then you hit this little deploy button. And actually what it does, it compiles the code, uploads it to the internet computer, and you can already easily write some of your code and experience the internet computer, experience running code on the blockchain here. Of course, like the code like this will only survive for a bit, otherwise it would clog everything up. But that's a very nice way to start coding. So go there. There's some rough edges still here because literally we did that over the last couple of weeks. But as you can see, I'm very excited about that one. Okay, so that's all about ICP. So maybe let's talk about why ICP is like a cool Bitcoin layer 2. And because the reason here is like a chain fusion, because on ICP, again, you can interact with any other chain or like many other chains. And yeah, let's talk about chain fusion. So chain fusion, there's a number of things here, but like the technical parts that really are necessary here is what we call chain key signature. So that's how, as a smart contract, you can own like a Bitcoin key, you can own an Ethereum key, you can own like a public key and sign authorized transactions with that. So that's like one part. The other part is network integration, because like it's not good enough if you sign things but you cannot talk to other blockchains. And network integration actually allows, integrates the ICP blockchain with other blockchains, that actually smart contracts on ICP can talk to all these other blockchains. And we already have quite a bunch of tabs that do that. Again, you can go on internetcomputer.org ecosystem to look for that. We actually also have like sort of bridging in quotes, because there's no bridge, because it's really native smart contracts. So there's like tokens that are like twin tokens on ICP that you can transact with on ICP very fast, profit from the fast transaction speed on to their native blockchains. As I said, we have like native integration with Bitcoin, we have EVM chains integration, and of course we have ICP here as well.